Hello, I'm with Team SG1. My name is Luke Funk. We're going to demonstrate a dynamics principle for you today. We're going to have Ben Gerwig explaining our diagram, Daniel Story going over our calculations, and Chase Zesh doing our demonstration and doing a little wrap up. So we did a problem from the section 17.1 or 17.3, excuse me, and it demonstrates translational motion. We'll also talk about slipping and tipping and friction.
Okay, my name is Ben, and I will be demonstrating or showing what our demonstration is going to be with a diagram here. And so if you have your textbook and you want to look at it, we're modeling this off of the 13th edition in 7.3. It's on example 17.7 on page 417. We're using the same setup as that. We've constructed our own block sliding along a board in order to demonstrate the slipping versus tipping. So in order to do this, we've got to get a constant force. We used a weight dropping off of a pulley so that it's constant force rather than just a constant speed. So the diagram here, we've got two things that can really be varied. We can change our height above the center of gravity that we're pulling the force with, and we can also change what force is being applied. And with changing those, we can get different scenarios with the reactive moments and whatnot to see if it's going to just slide or if it's going to tip while sliding.
My name is Daniel Story. I'm going to be talking to you guys about the calculations that we perform. So we do know the mass of the block. That's 532.7 grams. We also know the coefficient of friction that was measured at an earlier time using a motion detector and the same setup that we have. We were able to use the same equations and solve for the coefficient of friction. We also know the mass of the weights that we're going to be dropping off the pulley. The P we know because of doing the sum of the forces in the Y. For the mass of the weight, we were able to determine the tension force that's going to be pulling on the block, as you can see here. And we also know the distance that that's going to be acting from the center of gravity. So for this scenario, we actually have two cases. The crate can either tip or it can slide. If it's sliding, then we know that the coefficient of friction is equal to mu sub k times the normal force. So by using the sum of the forces in the y, we can get that the normal force equals the mass times gravity because the acceleration of the acceleration in the y direction is 0 because the block's not moving up or down. And so we know that the normal force equals 5.22 newtons. Using the sum of the forces in the x, by substituting in mu sub k in for the force of the friction, we can solve for the acceleration that it's moving at, and we know that the acceleration is 1.47 meters per second squared. And that compared to the 1.3 meters per second squared that we found in actual value is fairly similar. So in order to verify that our assumption is correct and that it's actually sliding, you have to do the sum of the forces or the sum of the moments about the center of gravity. And so we know that P is acting at a distance y from the center of gravity. We know that the normal force is acting at an unknown distance from the center of gravity. And then depending on where that normal force is acting, that'll determine whether or not it's tipping or just sliding. So if the normal force is at the very edge, it's tipping. If it's somewhere in the middle, then we know that it's sliding. So what we do here is we rearrange this equation, solve for the x distance that the normal force is acting at. We get that it's 1.278 inches, which is less than the 1.75, which we put at the end. So we know that it's not tipping, so therefore our assumption is correct. So the second thing that we're going to do is we're actually going to take it a step further, and we're going to calculate the amount of force that we need to apply to it in order to cause it to tip. And so we know that it tips when the distance that the normal force is acting away from the center of gravity is equal to 1.75. And so that would put the normal force at the very end, and so therefore it would be tipping. So we use the same equation, the sum of the moments about the center of gravity, and then instead of this time knowing the x, we know the x, and now we're looking for the force that we're applying onto it. And so by using all the same variables and everything, we find that the force has to be greater than 2.21 newtons in order to get it to start tipping. And so by doing some conversions and things like that, we can get that the mass that we need to load onto it is 225.02 grams.
Hey guys, I'm Chase, and I'm going to describe our test rig and then show you all the two cases. First off, here's our rig. We have our block, which you saw the diagram over earlier. Center of gravity is right there. Force is being pulled along this action right here. So when it's in motion, it'll look something like this. Notice the weight's down here, going around the pulley. It slides in this sort of way. So here we have case 1. We have 220 grams on the hanger here. The block is set back, the weights are up, so when that's released, the block will begin to slide and accelerate, and hopefully we will see no tipping. Let's release it. Notice there was no tipping, demonstration success. So here we have case 2. We have changed out the weights here. We now have over the amount to cause tipping. We calculated earlier to be 225 grams. So this is significantly over that so that the demonstration works properly. But once this is released, hopefully we'll see some tipping. Again, we saw tipping when it slid, demonstration success. So the reason we chose to go with a significantly higher amount of mass than what we had calculated was to demonstrate the degree of tipping significantly. If we had gone with something very close to what we had calculated, the block would only tip a very small degree. So it would have looked only like that maybe. So we went with a higher mass so that way in our demonstration it would actually tip up and it would be noticeable.